other items. Now, the construction of a sanitary can is really very simple. It consists of a body, a top, and a bottom. The dull gray material around the perimeter of the top and bottom pieces is a sealing compound, which acts as a gasket to make the can airtight. While a sanitary can seems uncomplicated, making them by the millions is another story. To produce the simple three-piece can economically and in the huge quantities demanded by a hungry world, high-speed, complicated equipment is required. Actually, two production. An end-line mill is first trimmed and then cut into scrolled sheets, ready for feeding to the strip feed press, where it is blanked and formed. The sheets are coated or lacquered on the side that will become the inside of the can. This protective coating is required on practically all sanitary cans. Most of the cost of a can lies in the tin plate, and a constant effort is made to save material by reducing scrap. Proper scrap layout determines the size of the tin plate sheet, and inasmuch as most all can ends are made in double dies, 2 per stroke, the strip delivered by the scroll shear is known as a double die scrolled strip. By interlocking the cuts in a strip of this type, significant savings in tin plate are accomplished, from 3 to 7%, depending on the size of the can end. Operation Can End starts with the automatic sheet feeder, which feeds sheets of tin plate to the first table of the scroll shear. On this table, each sheet is first located correctly by reciprocating side gauges. Feed bars advance the sheet to the 2 slitting cutters, which accurately trim and square the sheet on both sides, thus ensuring scrolled sheets of exact length and squareness. An air-operated sheet stop prevents the sheets from advancing into the slitting cutters until they have been positioned correctly. The sheets are then engaged by the feed bar and advanced to the cutters. A double sheet detector stops the machine if 2 sheets are accidentally fed to the first table. This first table is designed so that it can be retracted to permit the slitting cutters to be ground without removing them from their shafts. After the sheets are trimmed and squared, they are discharged to the second table of the scroll shear, where they are picked up by the feed bar for feeding to the scroll die. The feed bar is of the magnetic type, which carries the sheet slightly past the fixed stop fingers on the forward stroke. On the return stroke, the sheet is registered against the stop fingers, which ensures an extremely accurate width of the strip. On an average, 4 scroll strips are produced from each sheet of tin plate. The Bliss number 1103 scroll shear has been designed with an auxiliary mechanical feed bar, which eliminates the idle stroke between sheets. This feed bar rapidly advances each sheet so that it catches up with the sheet ahead. Thus, every stroke of the shear is a cutting stroke. In this operation, the machine is arranged so that the scrolled strips drop into one bin and the last strip from each sheet with the straight edge into the 4th or lowest bin. However, when desired, this arrangement can be changed and all strips collected in the top bin. In either case, scrap trimmed from the front edge of the sheet is kept separate. The double die scroll strips are now stacked for transfer to the strip feed press. The Bliss number 1831 strip feed press blanks and forms can ends in double dies. at speeds of from 250 to 325 strokes per minute. This means 500 to 650 can ends per minute. The scrolled strips are hand-loaded in an overhead long supply type of strip magazine. The strips are pulled from the bottom of the stack by suction cups and are then engaged by the cross-feed mechanism and carried down to the feed table, where the main feed bar can pick them up. The feed bar advances the strip at each stroke of the press the exact amount required for the particular die being run. Notice how the auxiliary feed bar engages the strip so as to advance it a pitch and a half for each stroke. This produces an overlap of incoming and outgoing strips and eliminates the idle stroke, thus ensuring that each stroke of the press produces 2 can ends. This is a typical can end double die, which blanks and forms 2 can ends at each stroke of the press. Here, through slow motion technique, we can see the overlapping of the incoming and outgoing strips, which enables the press to deliver 2 ends at each stroke. As the ends are stripped from the punches, they are contacted by mechanical kickers, which eject them to the rear. The scrap is automatically discharged to the side of the press by a timed roll-type scrap ejector. In addition to the regular controls, automatic electric stops are provided as a safeguard to the die and press and disengage the Bliss air friction clutch in the event of jams or double strips. The press is restarted at the main control panel. When the ends come from the 1831 press, they are completely formed except for the edge, which is only started. They are then automatically conveyed to a Bliss number 20 curler mounted at the rear of the press. Here the ends are completely curled and magnetically conveyed to high-speed automatic compound applying machines. Compound is applied just inside the curl of the end and ensures an airtight seal when the ends are double seamed to the can body. Following the compound operation, the ends are packed for transfer to the double seamer in the body line or to the closing operation at the packing plant. Although these operations, from blanking and forming to applying compound, take place at relatively high speeds, only one operator is needed to keep the line operating at top efficiency. This is made possible by the utilization of a unique conveying system. From the curlers, the can ends are discharged to a magnetic elevator that carries the ends to the top, from where they are conveyed back over the press to the compound machine. This allows the operator to be stationed between the press and the compound machines so that he has free access to each. So much for making can ends. Making can bodies is a more complex problem. However, the operation of a body line can be broken down into 4 basic steps. First step, produce a body blank from tin plate. Second step, form the body and solder the side seam. Third step, flange both ends of the body to take a top and bottom. And the fourth and final step, double seam the bottom to the body. So here are 4 seemingly simple steps that actually require many separate mechanical operations, performed at the amazing speed of 350 to 450 times a minute. This is a Bliss number 5325 duplex slitter with automatic sheet feeder. It produces body blanks to be fed to the body maker. This duplex slitter will take sheets as large as 44 by 44 inches. As the sheet is fed from the automatic sheet feeder onto the first operation table of the slitter, the two sides are trimmed and the sheet is slit into 3 strips. Passing on to the second table, the strips are individually picked up and carried to the second set of cutters where they are trimmed and slit to the required size. The blanks drop into the stacker, ready for transfer to the body maker. A closer examination of the various components will reveal the ingenious engineering and expert craftsmanship required to accomplish this high production rate. As the sheets are fed to the first operation table of the slitter, the table feed bar engages the sheet and pushes it toward the first operation cutters. Simultaneously, gauges on both sides of the table move in and position the sheet correctly. This ensures precise registry of both plain or lithographed sheets. These side gauges are equipped with rollers to permit easy passage of the sheets. The sheet then passes through the alloy steel cutters where it is trimmed on both sides and slit into 3 strips. From the cutter, the strips then pass to the second operation table. As the strips feed onto the second table, they strike a spring-backed side gauge, which automatically lines them up for the next step, which is cutting the body blanks. To advance the strips to the second slitter, a feed chain to which a number of metal fingers are attached is used. After strips drop into place, the fingers are raised slightly above the table by cams so that they can engage the back edge of each strip and feed them forward. To keep the strips above the feed chain fingers as they move across the table, magnetic rollers are used to lift the moving strips above the fingers. Hold downs press the back edge of each strip tight against the table, ensuring proper engagement with the advancing feed fingers. Final registration of the strips occurs before they reach the cutters. 2 back fingers on the feed bars pick each strip off the chain fingers. Immediately after, cam-actuated side gauges move in and complete the positioning of the strip before it enters the cutters. Finally, the strips are cut into body blanks and are dropped into the stacker. All of this complex movement is accomplished in a matter of seconds. In fact, a sheet of tin plate is cut into 24 body blanks every 1.5 seconds. Truly a very short time in which to accomplish this important first step, the making of a body blank. The Bliss number 603 body maker produces a can body with the side seam locked and soldered. The blanks are transferred to the body maker, and before insertion into the magazine, they are checked by the operator for squareness and size. Installation of regular change parts permit the number 603 body maker to produce all sizes of sanitary cans commonly used today. Sizes up to 6 3/16 inches diameter by 5 9/16 inches high can be produced with the normal change parts. Larger sizes up to 7 13/16 inches high require a slightly more involved change. The 603 performs 8 different operations: flexing, knurling, notching and edging, flux application, forming and side seaming, soldering. All controls are contained in one unit convenient to the operator. The blanks are pulled down from the magazine by suction cups and pushed into the flexor. Flexing breaks down the grain in the metal so that the finished body will be a perfect cylinder without flats on the sides. After the flexing operation, the blank is picked up by the feed fingers and carried through the knurling rolls. Both edges of the blank are knurled. Knurling ensures a better flow of solder. From the knurling station, the blank is carried to the notching station, where it is registered and one edge notched and the other edge slit. The notches and slits are necessary to provide a proper lap at each end of the side seam. The hooks are formed at the next station in a double action operation. After the blank is registered, one edge is formed up, the other down. The edge is first turned at a right angle, then formed inward to make a hook. At the next station, a rotating fiber brush applies flux to the edges in preparation for soldering, and the blank advances to the wing or forming station. At the wing station, several operations seem to take place simultaneously. Actually, there are 4 operations taking place, and timing is extremely close. By slowing up the action at this point, each operation can easily be seen. When the blank is advanced to the wing station, it is clamped on top of the horn. Next, the wings fold the blank around the horn. Both sides of the horn expand and lock the body hooks, after which the hammer comes up and sets or bumps the hook. Observe the expanding action of the horn as the blank is folded around it. The hammer comes up immediately and sets the hook. At this point, the body is now formed and is ready for the next step. As the body leaves the wing station, it is picked up by the chain dogs on the soldering attachment. The soldering attachment is an integral part of the body maker and also performs several functions. From the wing station, the can body is carried on to the water-cooled rail or horse, where it is first preheated. It then passes to the solder pot, where the solder roll applies solder to the seam. After soldering, the body is then post-heated to ensure flow of the solder through the entire seam. It is then passed over a wiper roll, and any excess solder is removed. To prevent solder from being thrown into the body during the wiping operation, a solder splash eliminator is usually used. This consists of a chain-driven series of baffles. The body now moves along the rail to a cooling section, where a blower forces cool air over the seam to set the solder. Passing further along the attachment, a roll turns the body 90 degrees before it enters the conveyor to the flanger. Occasionally, a body is removed from the line, inspected, and broken open in order to examine the soldered seam. As the bodies leave the body maker, they are conveyed to a Bliss number 1315 flanger. This is an 8-station rotary unit which flanges both ends of the bodies simultaneously. Precise feeding of the bodies to the flanger is ensured even though an interruption in production empties the feed-in chute. This precise feeding is accomplished by the use of a spiral feed which permits single cans to be fed to the machine in the same manner as when the chute is full. This prevents jamming and contributes to uninterrupted production. Now the body is flanged and ready for a top and bottom. From the flanger, the body again enters the conveyor where it is carried to the double seamer. Here, can ends are fed into the machine where they are attached to the body by folding the curled edge under the flange of the body and flattening it, thereby making a bottom. The body now becomes a can. The can again enters the conveyor system where it is carried to the Bliss number 304 air tester. This 36-head bucket-type tester is actually the watchdog of the can body line. It ensures delivery of perfect cans for the filling machine. Imperfect cans are quickly rejected, permitting the operator to correct any malfunction on the line. Here again, a spiral feed is used to ensure jam-proof feeding of the cans to the star wheel, regardless of whether the chute is filled or not. A plunger picks up the can from the star wheel and clamps it against a rubber disc. The bucket comes in over the can, leaving a small air or test space between the outer wall of the can and the inner wall of the bucket. The pressure in this space is normalized to atmospheric pressure before the test cycle starts. As the tester revolves, compressed air at a predetermined pressure is forced into the can. An imperfect seal between can bottom and body, or a faulty side seam, will allow the air under pressure to leak into the small space between can and bucket, causing a pressure rise in this space, which in turn actuates a sensitive detection and ejection device, resulting in the ejection of the imperfect can or leaker. The perfect cans leave the tester by way of the bottom chute. Any reject discharges by way of the top chute, where it is examined and rechecked in an air-water tester to determine why the can was deficient. An important part of an automatic can-making line is the conveying system and the controls used to operate it. In this line, cans are discharged from each machine to a pneumatic elevator. A powerful blower in the base raises the cans to the top of the elevator column, where they are discharged into a runway from which they drop by gravity to the next machine. Controls at various points throughout the system ensure the proper flow of cans from machine to machine under all circumstances. Proper flow of cans is also ensured by the action of the accumulator hanging above and between the flanger and double seamer. When all machines in the line are in operation, the cans pass directly through the accumulator. If operation of the seamer should be interrupted, the remainder of the line will continue to operate from 2 to 3 minutes, and the cans will be retained in the accumulator during this period. An ingenious arrangement of electric controls assures proper operation of the accumulator. After operation is resumed, the cans will be discharged from the accumulator and conveyed to the double seamer in the normal manner. The last step in the story of can making is closing the can, and this takes place in a packing plant at the filling line. At the packing plant, the can bodies and can tops are brought together to provide a strong, clean, and long-lasting container for the thousands of food products made available because of the airtight feature of this valuable and convenient container. After filling and sealing, the cans move on for additional processing, are labeled, packed, and shipped all over the world. The sanitary can is the bulwark of the food industry today, and E.W. Bliss is proud of its contribution to this industry, not only in the development of the most modern equipment available today, but also as a pioneer in automated can manufacturing equipment. With an eye to the future needs of the canning industry, Bliss, through research and development, is constantly seeking newer and better ways to improve can production, constantly producing newer and better equipment for all types of metal containers.